I'm Chris Monson. I met Walid Taha and his student at Rice University, and I'm pleased to host them here today. Raj Bandyopadhyay is one of Walid's students and works on compiling dynamic languages, specifically in this case Python, which is of course near and dear to everybody's heart. And I'll just leave the rest of the introduction to him.
Hi, everybody. I'm Raj, and I'm a graduate student at Rice University. I work with Dr. Walid Taha, who's also here and gave a talk earlier in this afternoon, and with Dr. Ken Kennedy, who's at Rice in the Department of Computer Science. So I'm here to talk about compiling Python in particular, but also let me tell you something about the work that our group does at Rice. Our group is part of work on what is known as telescoping languages, which is a larger effort to compile scripting languages like MATLAB, Python, R into compiled code and improve their performance. So we all know that scripting languages nowadays are pretty ubiquitous. Everyone's using them, particularly in scientific computing, but also for all kinds of uses. And Python in particular is being used, I've found, whenever I attend Python conferences, is being used everywhere for things as diverse as nuclear physics to financial modeling to everything else. So I've been looking at trying to compile Python for a while. And recently, in collaboration with Dr. Walid Taha, we came up with an interesting approach, which I'm going to talk about today. So we all know the pros of compiling or programming with scripting languages. It's easier to do, it's quicker, it's more productive, and it takes a lot less time than C, C++, and a lot less bugs, and all those good things. However, the cons, poor performance compared to C or Fortran. So you always have to implement your hard, difficult code in C, C++, Fortran, and then use it connect it up as a library, or glue it with Python or all these scripting languages. So our goal, our research in general of our group at Rice is to combine these two. We want to combine the productivity of scripting languages, in my case Python, with the performance of C and Fortran. For that purpose, we try to use a technology available in compilers. So traditionally, we want to compile these down to native code. Now, why is this a problem? It's usually a long and tedious process to write a compiler. We have a lot of language-specific optimizations, architecture-specific optimizations. So anytime you want to program for a different platform, you have to write a compiler for a different platform. Your whole compiler has to change. Your optimizations have to change, everything. It's prone to errors, bugs, requires a lot of testing. And so it's very platform-specific. We propose an alternative way of programming or writing a compiler. So my talk is not only going to focus on the specific work for Python that I'm doing, but also the methodology that we are proposing, which is to write a compiler by partly stealing the efforts of the functional programming world. So basically, we are going to translate Python to a typed functional language as an intermediate. And in our case, we are going to use OCaml as an intermediate language. Why and what are we doing here? So you might think, for people who are used to programming in C, C++, Fortran, as I was for a long time, functional programming was kind of this interesting thing, but it wasn't really practical. We thought it was too slow, and it was never going to be used in contexts where performance was needed. However, it's not really the case anymore. First of all, functional programming languages have very good memory management runtimes. They have good garbage collection and automatic memory management systems. So that, in fact, is perhaps the best reason to use functional languages as an intermediate for compiling a dynamic scripting language like Python, which relies a lot on garbage collection and does not expect the programmer to manage their own memory. They have highly expressive type systems, which can distinguish between boxed and unboxed values, can also handle both untyped or a range of computations ranging from untyped to statically typed computations. And as Walid talked earlier in his talk about resource-aware programming, there are extensions to OCaml and in the functional programming world, which can help in reasoning and verifying properties of a language as also of a compiler, which can help us in checking the correctness of the compiler, as also the correctness of the generated code. So here are these are only some of the reasons. We pick OCaml as our specific functional programming language to which we compile, or we want to compile Python. Why? First of all, it's a widely used language in the functional programming world. It's open source. It's available on all Unix distributions. It already has a pretty good native code compiler, and which works on multiple platforms. In the functional programming world, it's a strict language as opposed to lazy, which means it's a call by value, which kind of corresponds to most of our dynamic languages, such as Python. In addition to being a functional language, an important thing is OCaml also supports imperative features, such as sequencing. So you can put statements in a sequence. Side effects like assignment, you can have a reference type in OCaml, which allows you to modify values in place, which can be used to simulate assignment in Python or any other imperative language. It has exceptions which allow non-local control flow, such as it allows you to break control flow in the middle of a loop, and it allows you to return arbitrarily from a function, which many other functional languages don't allow. Also, OCaml has a very extensive standard library, which has a lot of data structures very well implemented, such as lists, arrays, hash tables, string manipulation. It provides type inference, so we don't have a need to generate or specify explicit typing annotations, like we don't have to specify like this is an int. We can specify specific types for variables, but we don't have to because the type inference will take care of it. And it's definitely a very easy language to program in. That in itself is a motivation. For instance, I've been working on this compiler since about 3 months now, and you'll see how far I've gotten. And I can attest that even coming from the C++ world, that this is a great language to program in, just because of its static typing and easier. It's very easy to debug, and it's very high productivity. Also, another very important feature that Python has, which people use Python for, are the foreign function interfaces. So we use Python a lot to interface with libraries in C, Fortran, and so on. And OCaml actually has those features. It has very well integrated ability to integrate well with other languages and libraries. So that is also a great correspondence with Python. This is not completely new. The idea of using a typed functional language as an intermediate has been proposed before. In particular, there are two projects that are ongoing work. One is the Fox project at Carnegie Mellon and the Flint project at Yale University. Both of these projects are trying to develop a standard intermediate language, a standard intermediate typed functional language for a general compiler. So what they try to do is in addition to developing a language, they also try to develop type systems which will allow one to express almost or basically anything that you might want to compile. So they want type systems that are very extensive and also focused on safety. So type systems that are very extensive allow you to express all kinds of features and also in a very safe manner. However, since we are compiling dynamic languages like Python, which do not have a lot of static type, which do not have almost any static type information actually, we can do with a simpler type system. So in fact, the type system of a language like OCaml is very sufficient for our purposes. Let me talk a little bit about the challenges that we have in compiling languages like Python. This will apply to a lot of other dynamic languages, even like MATLAB or R or whatever, a lot of other popular dynamic languages out there. Why are dynamic languages good? Because obviously, as we all know, languages like Python are very flexible, they are very easy to use. However, the variable types are never declared. They are created by binding. So in Python, you create a variable basically by assigning to it. So if you want to compile something completely down to native code, usually you need some sort of type inference. So you'll have to figure out at least some information about whether something's an integer, a float, or all kinds of other types. With Python being object-oriented, this becomes more interesting. Scoping rules in Python are kind of interesting. It's largely statically scoped. However, in theory, it's statically scoped. However, the dynamic features allow a lot of access. So you can change a lot of things within a class. For instance, within a class, you can change parents and base classes, a lot of other things. And you can do a lot of stuff within an environment by querying it and modifying it, which can lead to a lot of dynamic nature, for which the static scoping may not be completely defined. Also, it has nested scopes. You can have nested functions, which and scopes like global and local scopes, which makes scoping interesting. Other problems with dynamic languages, object sizes can change. So if you want to infer, say, something about a matrix or an array, you not only have to infer its type, but also the size or what kind of elements it contains and the size of that array, the length of that array, or the size of the matrix. Lists matrices may have elements appended dynamically. The chief problem in dynamic languages is memory management. So you have to have garbage collection, which is necessary for ensuring runtime safety. You could write garbage collectors in C, of course, but however, a lot of the times, garbage collectors written in C have to be conservative because they might have to chase pointers, and when you have pointers, you can't make a lot of assumptions, and which is why many existing languages like Java, Scheme, and the ML family, Haskell, so functional programming languages like that, or statically typed languages like Java, have a lot of efficient memory management systems. There are some challenges which are specific to Python for anybody who's trying to compile Python. First of all, there's reflection, which means you can add and delete methods and attributes to objects very dynamically, in particular classes. Then objects may be queried for type by using a type function, and using the dir function, you can query an object for its contents. In some cases, you can also modify the type and the contents. Then function calls are an interesting challenge because function calls are very flexible in Python. There are positional arguments, there are keyword arguments, there are the star and star arguments, which allow for variable number of parameters to be passed around. And processing all these can make function calls quite expensive compared to a simpler function calling mechanism. Exception handling is it's kind of a standard feature available in a lot of languages, but in Python you also have a stack trace which you supply when there is an exception. Deletion and finalization methods, so you can dynamically delete stuff around from a module or a class. And you can also pickle and marshal objects using a representation of an object. There's a representation function which allows you to load and save objects and pickle them. So now that we have talked about the challenges in compiling Python, let me talk a little bit about my implementation of a compiler. This is a work in progress, as I said, so there are still a lot of things that are not done, a lot of things to be done, and a few things that we have done. So I'll kind of give an overview of that. So I'm implementing the compiler in OCaml. So I have a compiler that I'm writing in OCaml, and I'm translating Python to OCaml. To maintain the Python semantics, which can be pretty complicated, first of all, I'm basing my design on the Python reference manual and loosely structuring my compiler or designing my architecture based on the current Python implementation, which is CPython, which is the standard Python interpreter. So the way I do it is I define a base object type, which I'll come to in a bit, and all objects, which is like integer, list, classes, etc., and their instances are copies of this base object type. This base object is implemented as an OCaml record. For the dictionary, which is a very critical component in Python, I use an OCaml hash table. Now, for anyone who's used Python, you have an idea of how critical dictionaries are. Dictionaries are basically what gives Python its dynamic nature, which allows you to delete and add attributes to classes and all the dynamic stuff that you do. So it's very critical that we have a good dictionary implementation. Actually, OCaml hash tables that we have found are quite efficient for the purpose, and they actually perform quite well. For lists and tuples, I use OCaml arrays. So these are some of the data structures that I use. For instance, I can show how I implement a typical object, a typical Python object. Here, for example, is a list object in my OCaml implementation. It is kind of based on the CPython implementation of the type structure, and I've chosen to keep and eliminate some fields from that based on what I think is needed, but of course this will change as my implementation grows. So first of all, there is an object ID, which is the object identity. Now, in Python, every object has an identity, a type, and a value, as per the Python reference manual. Now, the identity can be, usually it's supposed to be the memory location. However, in our case, we don't really know if we can stick to that right now, because having the memory location as identity leads to memory management issues with the garbage collector. So we decided to, for now, to just allocate or have a counter and every object is given a unique integer identity. Every object that we generate in the system is given a unique integer identity. The value is basically an OCaml data structure representing whatever the internal representation of our structure of our object is. So for instance, this is a list. So when I create a new list object, I'm basically creating an array of, in this case, of size 0. And this is basically an OCaml constructor defining the type, that this is an array of objects. And here is, I have a null object in the system, which is basically a dummy object. So I'm creating an array of size 0 of dummy objects here. Then type is also a similar object with a similar data structure, and it represents the type of this object, the list, which there is a list type object representing this type. The dictionary is basically an OCaml hash table. This is a list of base classes or base objects. In case of a class, this will be the list of base classes. And in case of classes with multiple inheritance, this list is created by using the method resolution order in Python, the C3 method resolution. Then in case this object is a function, it would be a callable object, and we would actually have the code for the function here in this object call field. But this is not a callable, so the is callable here is false. This is a sequence object, so the is sequence is true, and this represents a sequence of length 0. There are some other fields which apply to very specific objects and represent particular properties. And this is mostly based on the CPython description of the type structure. So it kind of follows more or less the same things. So here's the general architecture of my translator or the compiler as it is now. So there is a Python code which gets translated by a parser to a representation of a Python AST. Now this representation is basically an OCaml data type, and which represents all the nodes of the Python AST. In case of the parser, I currently, I have an intermediate step where I use the Python's CPython's parser to create an intermediate representation of the AST and then go to my own representation of the AST. This is just so that I started writing a parser and lexer completely from scratch, but I found that it might be difficult to stick or make sure that I have the semantics down correctly, so just decided to stick with the Python parser for now. Then from the Python AST, I have my translator converts it to an OCaml AST, which is an abstract representation of an OCaml program, again defined by an OCaml data type. And this is a step where this is a pretty complex step where a lot of the actual work is done. Then there's a code generation step, which basically just takes the OCaml AST, converts to OCaml code. Now this is a runtime environment that I had to write in OCaml. This basically is the Python runtime environment. We had to define all the Python base types and all the various basic objects like lists and tuples and all the functions for Python. So this is again a pretty large piece of code, and which basically describes all of Python. It's currently not complete, but it has a lot of the Python basic object hierarchy in there. And when I have OCaml code, I basically use the existing OCaml native code compiler and linker and create the final native code for a given platform, which I can run. So during the translation, I first create a symbol table and scope analysis and do some scope analysis to figure out all the nested scopes and what are the variables in different scopes. So this is based on the compiler.symbols module, which is currently in the CPython distribution. And while translating it to OCaml, it's pretty straightforward. Just walk over the AST, and you have to create, as per the Python semantics, have to create new scopes for modules, classes, functions, and lambdas. Now, lambdas in Python, as we know, are basically shortcuts for function definitions. I don't perform too many optimizations right now. We do not perform any serious compiler optimization, mainly pretty simple things, which, again, some of which are done in the Python distribution already. For instance, a simple optimization is to store the first 100 integers as objects. So whenever you refer to any of the first 100 integers, you do not create a new object. You just refer to the existing object in the runtime. Then if you have constants in a program, so this is a run that I do just before generating code. If I walk over the AST to find out all the constants in the program, whether it's strings, integers, floats, and create one object per constant, which I have at the beginning of the generated code. So in that case, you're not creating multiple objects. However, there is enormous scope for serious optimizations at both the Python level and the OCaml level. For instance, a simple intuitive optimization which would seem to give a lot of benefits is constant propagation. Because according to the semantics of Python, if you're adding two constants, even two integers, you'd have to create integer objects for each of them and then add them and create a new object. Now, any sort of memory operations obviously would be expensive. So it would be great if you could remove some of those extra memory operations and derive results at compile time and substitute and have fewer object creation at runtime. Of course, this optimization in Python, compiler optimizations are much harder than in languages like C or Fortran or Java because of the very dynamic nature of the language, which can strike at pretty much any time and in any way. Of course, we are currently looking at optimizations that might be enabled by SSA form and type inference. And we think that these would be necessary steps sort of to do before performing any serious optimizations. However, this is, again, kind of where we are at right now, and we're looking for ideas on how to actually implement those. So current status of this compiler, most of the basic object hierarchy has been implemented by me. So I have all the basic objects like int, float, bool, list, tuple, dix, class, and most of their properties implemented. Language features like loops, ranges, slice subscripts, attributes, class attributes, operators, nested scopes, globals, exceptions. Again, yeah, most of them have been implemented. I believe, I've run it on a lot of benchmarks, a lot of test cases, but this definitely I cannot say for sure that this has been exhaustively implemented because Python has a lot of tricky features which I'll keep discovering and sorting out as time goes by. Hopefully, get it done as quick as possible. There are some important features that I still have to implement. For instance, right now for functions, I handle positional arguments and keyword arguments, but do not handle star and star star arguments yet. Again, the way I do functions is, in order to optimize or speed up function execution, whenever a function is called, I check for special cases. So first check if there's only check for the case where there are only positional arguments and positional parameters. That it makes a lot of difference because you do not have to do all the massaging for the keywords. Then check for the case where there are only positional and keywords and none of these star and star star. So I do not think that when I implement the star and star star arguments, it will affect the performance a lot. But again, that's just my prediction. I do not implement list comprehensions and generators so far. I have not done that, but I do intend to do it. Then modules and import is something I'm working on. Deletion methods, and one of the most important things, interfacing with C and other languages.
I'm missing exec and eval from either this slide or the previous slide.
I beg your pardon?
Exec and eval.
Yes, I am.
This one or the last one?
This one. Thank you. Okay, Hiro's question was, there are features in Python called exec and eval, which allow you to execute foreign functions. So yes, it's on this side. This slide is not yet implemented. I should have written that or considered that. Sorry. Here are some preliminary results. Again, I would not put too much weight on them because benchmarks are not that significant until you have a complete compiler. But still, as a preliminary result, it's kind of encouraging. All the benchmarks except for the last one are taken from the PyBench suite, which basically has For each benchmark, for instance, if you look at, I don't know, I'll pick a random one, integer operations, it's basically a bunch of addition, subtraction, multiplications on integers done in a loop, in a big loop, and executed lots of times. And so for each of these benchmarks, when I compiled and ran them, I found certain things which helped in speeding it up, which is what the comments indicates. For instance, I found that storing the first 100 integers helped a lot in this benchmark. For lists, the way I'm implementing lists is, again, similar to the optimization done in CPython, where the list is stored as an array of fixed size. But when you need more space, or when you need to set or store an element at an index which is higher than what you have, you just duplicate that array, create a new array with double the size, and use that. So that is something which the idea which basically is done in CPython, and I kind of just use that idea. Tuples, I do not get a lot of speed up because the tuple benchmark tests a lot of slicing, and slicing is quite an expensive operation, at least the way I've implemented it. Loops and if statements do pretty well, but this was only after I implemented the range and xrange function in Python, which gives you a range of xrange gives you a range of integers which you can iterate over, whereas range gives you a list of integers which you can iterate over. And function calls, you get the speed up only after you consider special cases. Dictionary operations, something that made a big difference was using a smaller key size. So at first I was using an entire object so if I wanted to look up an attribute, I was using the entire object as a key for the dictionary, which I changed that to use the object identity as the key, and that made a lot of difference in the speed. The final benchmark is something called PyStone. This is a much more realistic complex benchmark, I would say, where it has a suite of functions which do different things. Some of those functions perform arithmetic operations on integers and floats. Some of those functions perform copies of classes and assignments and deletions, assignments to attributes and retrieval of attributes. Here I have not got as good a speed up as I would like. And after profiling and a lot of study, I found that I do still have some bottlenecks in accessing attributes, and particularly in setting attributes. And when I create a lot of objects, I am running into some problems with garbage collection, and because the garbage collection is getting very enthusiastic in OCaml. So we know that there are some issues that need to be resolved at this stage. So I'll just give a summary in conclusion of the ongoing work. So far, there are some preliminary results that are encouraging, but a lot of work needs to be done. I still need to implement a lot of more of the complicated language features, like meta classes and things like support for modules, importing modules, foreign function interfaces, and all that. Need to work on memory usage by minimizing unnecessary copying and lookups, which is a problem in a lot of dynamic languages, where objects are copied far more excessively than they should. In fact, there is a group at Rice who's working specifically on in-place algorithms for minimizing copying of objects in dynamic languages. And I need to look at more compiler optimization techniques. So currently, the roadmap for the next period of time that I'll be working on this is basically trying to complete complete the implementation of all the language features in Python, look at optimizations for higher performance, translate all the standard library of once I have those things, I can translate all the standard library of Python to native code, and I'll be able to compile more realistic programs in Python after that, and then the external function in language interfaces. So this is kind of my talk for now, and this is kind of just some ideas and just give an overview of the current state of my work at Rice University. So I'd be glad to take any questions and also any feedback and ideas that you may have, because I know a lot of you guys use Python seriously, so it'd be great to hear what you guys think of this work and what you think I should do. Yes?
I have a question about the optimization you made to store the first 100 integers.
Yes.
You mentioned it earlier in the talk, but then on the optimization page, you said that you made the optimization in response to the results you were getting in the first benchmark.
Right.
Do you think that optimization would help Python programs in general, or just that benchmark?
Well, again, it depends on how programs are used, but of course, if you're storing, I kind of experimented with this a little bit. If you are storing, the first 100 integers, now you have to make an assumption that your program kind of uses the first 100 integers only and doesn't use anything else. Of course, if you have a program like that, it would help a lot, because then for every new integer that you use, you won't have to create a new object. So yeah, it will help for some programs. It won't help I can't say that it'll speed up every Python program in general, because it would depend on the specific usage. Again, I think the number 100 is kind of arbitrary. I tried 1,000 and 10,000, but what happens is that when you start up the runtime, there is some overhead in creating the first, this array. So again, if you're running a very large program in Python, it would probably help to create store an even larger number of integers. But if not, yeah.
I can't remember. Is this done by CPython as well?
Yes, it's actually, yeah.
I wanted to offer one data point you may want to play with. In my open source package, Gimpy, which is, I believe, now available in third source, Chip Turner is working on releasing it. You actually get to play with those kind of how many you want to cache at start and so on. I've experimented pretty extensively, essentially in the field of combinatorial arithmetic, because that's what I originally made Gimpy for. It's my hobby. I do combinatorial arithmetic, probability computations. It so happens that somewhere between 50 and 200 seems to be a pretty sweet spot for that. You don't really gain all that much pushing further, and don't save all that much getting further. So the 100, which I assume Guido, I assume you just pulled it out of a hat, right? You didn't do benchmarking to see how many. It seemed to be a pretty lucky choice. It's for like that kind of programs where you do a lot of computation. Sure, you'd like many more, but then you're overwhelming your caches, memory caches, and so on.
Thank you.
But with Gimpy, you get to play with that very extensively and see what happens.
Thank you.
So just to be clear, that particular optimization is done in CPython. So it was not something.
Yeah, let me repeat what just went on. So the gentleman here just said that he has experimented a lot with his package on optimizations, and he finds that a number between 50 and 200 is probably a sweet spot if you want to store a set of integers in advance, 50 and 200, so 100 is a good choice. And also, what Wally just said reminded us was that this is not an optimization that I picked out myself, but I kind of got it from the Python interpreter, so CPython already does that optimization. Any more questions, feedback? Yes, please.
So it's a nice roadmap. What's the rough timeline of the
project? I started working on this whole thing in late August, and I've been basically working on this since then, except for Christmas break. So it's actually would be considered a very good timeline for a compiler writer. So I do think that writing a compiler in this methodology is pretty productive. Yes?
So it seems like a lot of Python's dynamic features require a lot of hash table lookups.
Yes, that's how it's.
To what degree is that a bottleneck in the efficiency you get, and to what degree can you statically tell that, okay, these variables, these fields, I won't have to do any hash table lookups on, I can get the direct object?
Excellent question. So I'll repeat the question for the benefit of the audience. A lot of Python's dynamic nature comes due to its hash table, because everything in Python is based on hash table. It's a very important structure. So the question is that to what extent can we reduce the number of lookups by statically predicting or inferring that certain variables are accessed in certain ways? Now, we were actually talking with Hido over lunch at this, and this is an extremely hard problem, in particular in case of Python, because it is just such a dynamic language, and things can be modified at any part of a program by anything else practically. So the only way we can confidently say or do something like this is performing a whole program analysis. It's very difficult to analyze things like a class by class or function by function and say, okay, this function will never be affected by anything else, or this class will never be affected by anything else unless you perform a whole program analysis. However, if by performing whole program analysis, you can deduce that certain classes or functions are not touched by external entities, then it would be far more possible to focus on those individually and then perform some sort of analysis to say, okay, this variable is not modified in this class or modified at this point and not after that. So we can, every time it's looked up after this point, we can just, we cannot do a hash table lookup, but use a stored value. So it will take a lot of compiler analysis for this. Yes?
Have you considered not supporting features like executive eval and base class assignment or base switching compilers? Like if you notice that the programmer is using those features to switch to a more conservative but slower compiler?
Interesting point again. The question is, have I considered not supporting some features and making a more restricted compiler, which I use in some cases, and using the full-blown compiler when I know that a programmer is using certain features like exec and eval? That's definitely something to look at. So far, our goal is to support the entire Python language because we want to do that, and we also want to justify this methodology of translating it to a functional language. But that's definitely something to consider in case of performance. Yes.
One other thing, I don't know the state of OCaml with concurrency stuff, but does OCaml have like concurrency primitives, and could you use that for Python threads?
I am not aware of that. The question is, does OCaml have concurrency primitives? I think Walid might be a better expert on that. Do you know about that?
So there's some support for lightweight threads. So OCaml has some support for lightweight threads, but there are some limitations with concurrency in the built-in libraries.
Can't hear.
I think, yeah.
Well, I'll just repeat. OCaml has some support for concurrent threads, but it's not that complete, I guess.
You couldn't necessarily just drop the Python thread module and have that and have it actually.
That's again interesting. Again, the suggestion is to have multi-threaded version of. Is that what you're talking about? Having different threads?
I know. I mean, of course, the CPython uses OS level threads.
Okay.
I don't know how many assumptions are out there that would make it possible to use runtime threads.
Okay, I have not looked at the idea of runtime threads yet. I have not considered it, but it's definitely something that I can look at. Anything else? Yes.
Okay, it's working. I'll take advantage of my microphone holding status. So I noticed that you had an optimization in dictionaries where you used the object ID because you wanted to use shorter keys. Now, in general, dictionaries are not keyed on the ID of the object, but rather on a double under hash function or something like that. And so I was wondering if you could explain a little more about what that meant, because that seems a little alarming, I guess, on the surface.
Well, as far as my understanding of Python semantics goes, that an object once created does not really change its identity. So the problem that I run into is when I started hashing or started using dictionaries and benchmarking them, I found that they were too slow. And the reason for that was that using an entire object as my dictionary key was slowing it down because it was slowing down the hash function. And this may be something specific to the way OCaml implements its hash function. I can change that. I can use that.
It looks like Walid wants to say something.
Yeah,
else.
literally.
So if I understand correctly, you're saying that having the dictionary lookups being based on the object ID, whichever way it's defined, is not exactly how Python does it.
Okay.
And that seems to be, a really interesting semantic issue that I wasn't aware of before. And it's very likely, actually, that Raj also wasn't aware of it. That is probably something that, will make our semantics more correct. I don't think that we were able to find this in the documentation. Probably we could have been able to discern it from the implementation of CPython, but it's not something that we knew how it's done exactly until you said it now. So this is very useful information.
Thank you. Any more questions, feedback? Yes?
I mean, maybe this isn't exactly what he's asking, but for object and value semantics, like numbers and strings and stuff, have two of them which are supposed to hash the same, but do have different IDs just because they're allocated different clients.
Yes.
I think, so how do you hash those to the same place?
So what the question is that if I have two objects with the same value, or representing, say they're both representing the same integer, and since they have been created at different times, how do I make sure that I hash them to the same place? So if there is a constant that is in the program, like if I say x equal to 3 at some point, I have created one object representing the number 3 at the beginning of the program, and I refer to that throughout the program. And any assignments refer to the same object. So, I beg your pardon?
If you intern strings, then you get the same.
Right. Yeah. Yeah.
What about things which are not strings or integers that are still
I haven't run into a problem with that yet, but I might. That's something I'll look at. Thank you. Anything else? Questions, comments? Yes.
Who else is working on this besides yourself?
Well, right now I'm the only person implementing this, and Waleed and Ken are my advisors right there, and. But in terms of implementation, I'm the one doing it right now.
Who's helping you test your stuff?
It's all me.
You need help?
Sure. You want it? That would be great. Are you interested in trying out my stuff?
Sure.
That would be really great.
I'm not speaking just for myself. I'm sure there are a number of partners who are interested.
That would be really awesome.
That would be wonderful.
Yeah. I mean, I'd be glad to release a version of my thing on the web. It's still pretty, incomplete, but it works for the features that it works for, and I'd be glad to release it and have people test it and try it out and give feedback. That'd be really awesome. Could you come to me after the talk and talk to me? I'd love to take your email down. Yes.
Do you have a strategy yet for implementing generators?
No. Question. Oh, question. Do I have a strategy for implementing generators yet? No. That's my answer. Yeah. It's on my list, of course. All right. I guess that's it. Thank you very much for your feedback. If you want to come talk to me afterwards, if you're interested in trying out this stuff, then please give me your email address, and I'll be glad to send you whatever I have right now. And thank you very much for coming to the talk and all your feedback.